What is up guys, Elliot Waite here, and in today's video I want to show you how you can take a model you've trained in PyTorch and use it directly in the browser using JavaScript, like this. So here's an example of something I built, and it's basically the MNIST model predicting what number you draw. So you can see how quickly it's guessing each time the picture updates, it will make a new prediction. So that's one of the first advantages of having a model in the browser. You avoid the latency of having to send the data to the server and back. So you can get this really responsive app with really quick predictions. So the second benefit is that it's really easy to set up your website. You can do it with just static files, and that makes it really easy to scale. If you have a ton of users, you only have to serve those static files, and you don't have to start up new nodes of your backend server and handle load balancing as you get more and more requests. The third benefit of running your model in the browser is that it will work offline. And this is because you're not communicating with a backend server. So all the code you need to calculate the predictions to run your input through the model is right there already loaded the first time you load the website, or if you're using the JavaScript files in an app, as long as they've already installed the app, then they'll be able to use it offline. And the fourth main benefit is privacy. Since you don't have to send the user data off to a server, you can keep it right there on the local device, and you can let the users know that if you're handling sensitive data, you're not going to send it to a server, no one could potentially intercept it. And depending on what kind of data you're processing, that could be a really nice feature. So with all those benefits, there are only a few reasons you probably wouldn't want to run a model in the browser. And the first one is if you have a really big model. If it takes a long time to initially download the first page or download your app, that probably won't work, and you'll just have to keep it on the back end and send data to and from that server to run your predictions. So the second reason you wouldn't want to run a model in the browser is that the computation may take too much time. So even though the model may be small enough to download in a reasonable time, it might still take too long to run predictions on the user's device, especially since devices can range in performance, and you may want the app to work well across all devices. So in that case, you may get better overall performance by hosting the model on a backend server. And the third reason you may not want to run your model in the browser is that you want to keep the model private. So if you're going to run the model in the browser, they're going to be able to potentially inspect the graph, inspect the parameters, and use that model themselves. So if you want to keep it as your company's trade secret, then you probably don't want to host your model in a browser. So that's the other side of privacy. In the browser, you get user privacy, don't have to send the user data, but if you host it on a backend, you get model privacy. So now I'm going to show you how to actually convert your PyTorch models into JavaScript. And we're going to start with the PyTorch example MNIST code. And MNIST is just a model for recognizing handwritten digits. So I'm not going to go over all the code in the script. You can check it out on GitHub. I'll link to it in the video description. But we'll go over a high-level overview of what the model's doing. So we'll start off with our image, which is 28 pixels wide by 28 pixels tall. And since it's in black and white, we only have one channel depth of color. And we'll do a convolution on this image to get 32 channels in the second tensor. And we'll do a ReLU activation on this tensor. And then we'll do another convolution to get 64 channels. We'll then do a max pool on this tensor, cutting the height and width by half. We'll then perform dropout on this tensor of 25%, and then flatten it down and do a fully connected matrix multiply to get this intermediate vector of 128 values. And then again, we'll do a ReLU activation on it, another dropout of 50% this time. We'll then do another fully connected matrix multiply to get our final 10 values that we'll run a softmax on to get our 10 predictions for the numbers 0 through 9 for what we think the input image was. So now to the code. All right, first thing we're going to change is where the data is imported, just so it'll be in the same folder. And then I'm going to make it so it'll always save the model at the end, and I'm just going to call it PyTorch model. So now that we have our trained model, we have to convert it into something that can be used in JavaScript. So there are two ways to do this. We can go for using TensorFlow.js or ONNXjs. Now, the ONNXjs one is simpler, but it only allows you to do inference. So if you want to do training in the browser, I'd suggest going with TensorFlow.js. But if you're only doing inference, if you're only running data through the model, then ONNXjs is simpler, and I think it is more performant. So ONNX is the yellow, blue is TensorFlow.js, orange is Keras.js, and the height is the time to run inference. And the left side is on a CPU, and the right side is on a GPU, and their benchmark is the ResNet 50 model. So what is ONNX? It stands for Open Neural Network Exchange, and the short description on their website is actually pretty good. It says ONNX is an open format built to represent machine learning models. ONNX defines a common set of operators, the building blocks of machine learning and deep learning models, in a common file format to enable AI developers to use models with a variety of frameworks, tools, runtimes, and compilers. So they basically define a format in which you can specify your model and the parameters used in your model so that you can transfer it around. So if we save our PyTorch model in this ONNX file format, we can then load that file into ONNX.js. And ONNX.js is just a JavaScript library for loading these ONNX models and running inference on them. And it can be run anywhere where JavaScript can be used. So in a browser, using Node.js, or in an app using a web view. So here's the code for converting our PyTorch model to an ONNX model, and it's actually pretty simple. So first we're going to import our neural network, which we defined in our training script, which is here. So this is just a PyTorch module. And then we're going to instantiate that model. We'll then set the parameters of that model to the parameters that we got when we finished training the model using the loadStateDict method. We'll then put the model in evaluation mode, which is what you want to do when you run inference on the model. And in this case, it will essentially bypass those dropout operations. We'll then create a dummy input, which is just a tensor that has the same shape as the input that your model would expect. And it can have any values. And in this case, we're just going to use zeros. We'll then call the torch ONNX export method, which expects an instance of the model, a dummy input tensor, the path to where you want to save the output model, and an optional verbose argument, which, if true, will just print out a string representation of the graph of your model, as you'll see in a second. So here we'll run this, and it creates our ONNX model. And here's the output string, which is a description of the graph of your model. And it kind of shows you the format that ONNX uses. So I created this little demo script to test out using our model, just to make sure everything works before using it in a bigger application. And it's just an HTML document with some JavaScript inside. And we start off by importing the ONNXjs library. And that's going to give us access to these ONNX variables. And then we're going to declare this test function, and we'll call it right after we declare it, but we want it to be an asynchronous function because we're going to be using these await operators. So we'll start off by creating a session using this new ONNX inference session. And I'm not going to go over all the details of how the API works. You can check it out online for all the specifics, but I'll just walk you through this demo to give you an idea of how it works. So first we create a session, and next we're going to load the model into the session. And that's going to be done by specifying the path to the model. And this will return a promise that will resolve once the model's been loaded. So that's why we use the await operator. And then we're going to create the input that will pass through the model. And we do that with the ONNX.tensor class. We're going to specify a float32 array of this size, of this type, and of this shape, which our model is expecting. Then we're going to pass it through the model, and that's going to return a promise that will resolve once the model has calculated the output. So we'll use the await operator here, and that'll give us an output map. And then the reason this is an array is we could have multiple inputs here. If we look back at our forward pass, we're only passing in a single value. But for some reason, we're passing in multiple values. We could do that here. Oh, whoa. So this value will be a read-only map. And again, if we had multiple outputs, we could access them through this map. But since we only have one output, we'll just access the first value, and we'll do that by calling .values.next tensor.value to get the first output. That'll be a tensor. And then to access the underlying data, we just call output tensor.data, and that will return a JavaScript float32 array, and we'll log that to the console. Now, if we run this in a browser, we'll see we get an error. Cannot resolve operator log softmax. What this error message is saying is that ONNXjs doesn't currently support the log softmax operator. And if we go to this ONNXjs docs operators page inside their GitHub repo, we can see the operators that are supported. And if we go down to log softmax, we'll see that it currently is not supported by any versions. And if we look back at our model, we can see that at the very end of our forward pass, we call log softmax right here. But to actually get the probabilities we want, we don't need to call log softmax. We actually only need to call softmax. And as we can see, ONNXjs does support the softmax operator. So we can just update this model and create a new ONNX model from it and try that out. So I'm not going to do that in this file. I'm going to keep this file as is. I'm going to create a new Python file, which I'll call inference MNIST model. And here we'll update the model to be softmax. And then in our convert to ONNX script, we can change this to our inference model. And since changing this operator doesn't change any of the modules which require parameters, we can still use our old trained model and just reload it into this new model. So if we rerun this script, we'll get our new ONNX model. We can load it into here, overwrite the old version, come back to this page, reload, and now we see our output tensor, and those are 10 probabilities, what we want, just based off of an input of all zeros. Now, to be able to test out actually sending handwritten digits through our model, I've created this demo website. And it's just this canvas where you can draw numbers and it'll print out the predictions down here. And right now, it's not fully working because I'll show you something that we have in the code that we have to fix. So I'm not going to go over all the code. There'll be a link in the description to this code sandbox, and you can look over it. But at a high level, we just have all these HTML elements, and then we're going to load in our ONNX.js library and call our script file. And our script file will do some things to set up the canvas and set up the drawing. But what we're going to look at is the same code we used before, where we create a session and then we load the model into that session. And this will return a promise that will just resolve once the model's actually been loaded. So lower down here in our code where we actually do our predictions, we're going to make sure the model has loaded before trying to run any data through it. But up here is where we actually create the input tensor. And you can look at all the code around it. It's basically saying anytime the drawing is updated by adding a new line, we're going to update our predictions. So we come into here, and we're going to get our data from the canvas. And basically, we're going to get this entire canvas, which is 280 pixels wide by 280 pixels tall. And then we're going to try to run that through our model. Now, you could try to use JavaScript to convert that into the input format that we're looking for, which is a 28 by 28 pixel image. But there's actually another way to do it that I think is simpler, and that is to just change our model again, our inference model. So right here, the input it expects is a shape of 1, 1, 28, 28. But the actual shape we're going to get from the image data is just going to be a long list of all the numbers that make up this image. We have 280 pixels by 280 pixels, and for each pixel, we have 4 channels, a red, green, blue, and an alpha channel. So we're going to have to update our code to handle that. So if we look back at the model, I've added in this code. So this input x value is just going to be the list of numbers of the image data. So we're first just going to reshape it into this shape, 280 by 280 by 4. So that's the height, the width, and then the number of channels for red, green, blue, and then the alpha channel. And whenever you draw on a canvas, wherever you draw will get an alpha value of 255, and wherever you haven't drawn will have an alpha value of 0. So we can just use that value to figure out where we've drawn. So we're going to extract the fourth channel, which has an index value of 3. And then in this next line, we're going to reshape this tensor into the shape that PyTorch expects for images. And that's this first value is the batch size, the number of channels, and then the height and the width of the image. So we're then going to call the average pool operator, which will essentially resize this down by a factor of 10. So we'll go from 280 by 280 to 28 by 28, which is the size of the input that our model expects. And then since our max alpha channel value can be 255, we're going to divide that tensor by 255, and that'll bring our image values into the range of 0 to 1. But there's actually one more thing we have to do. So if we look back at the script that we used to train the model, I didn't mention this earlier, but when we create the data set, we actually normalize it before passing it in through the model, which means we take the initial values and then subtract the mean of the data set, which is this value here, and then divide it by the standard deviation of the data set, which is this number here. So we're actually going to have to do that with our data that we pass into the model as well. So if we look back at the model code now, I've copied over those values, the mean and standard deviation, and then just added in this last line where we subtract the mean and then divide by the standard deviation. And now we just need to recreate the ONNX file with this new model format. So we come over here, we rerun our script, but we get an error. It says shape 280 by 280 by 4 is invalid for an input size of 784. So the reason we got this error message is because we need to update our dummy input. It still is the shape of the original data that we trained on. We want to change it to the shape of the canvas data, which is 280 by 280 by 4. And it's all in one long list, so it's just going to be a single dimension. And now it works. So we got our new ONNX model, and we'll upload that into our demo code. So I just tried out the model on the demo and it wasn't working, and I was getting some errors with the ONNX.js. So I had to come back into the model and try a couple different things. And what I found actually fixed it was changing these two lines. So originally I was taking a slice like this, and when I changed it to taking a slice using narrow, that solved an issue. And then also on the average pool, I had to specify the stride. So if you look at the PyTorch documentation, if stride is left as none, it should default to the kernel size. But sometimes the conversion from PyTorch to ONNX.js can be a little finicky. And so sometimes you just gotta try debugging your model by creating a little small test like this and then incrementally changing things and seeing when it breaks and seeing if there's any alternative way of having the same operation be performed in your model using a different function. And now with this updated model, if we look back at our demo code, it's now working. We got numbers. Oh, that's 1, but it thought it was a 6. So, thought it was a 4. All right, so what's going on? So it's a little, okay. It's doing something, but for some reason it's not getting the best results. It's a 9, but the last one I thought it was a 4. So we're going to do something to improve the model a little bit by using data augmentation. And basically what that means is we're going to take the training data and shift it around a bunch before sending it through the model so that it'll be a bit more robust to the input looking a little different than what it's expecting. So if we look at the data in the MNIST dataset, we can see that these numbers are pretty varied, but they're all mostly in the center and the full height. And we're going to start by augmenting it by adding in some rotations. So we can see they got a bit more rotated. And then we're going to see what happens if we add in a translation. So that translated it vertically. We could also translate it both horizontally and vertically, which looks like this. And then we could also experiment with changing the scale. So that will give us some big numbers, some small numbers. And we can also apply some shear transformations, which looks like this. And then if we combine all those together into one, we end up getting some pretty tough samples for it to learn from. But if the model can learn to recognize these digits, it will be pretty robust and it should work better on our demo. So I've added those transformations to our training script right here in defining our training data. And now we're going to retrain the model from scratch. All right, guys, I've uploaded the new model, and when we test it out, let's see, is it more robust? Well, got that, got the 8, 9, got the 1, 0. Let's see if we even put a little 0 down here. A little less confused, a little more confused, but still doing well. 2, I think it's a 3. 2, 4. Oh, thinks that's a 7. Okay, so it could be better, but we're just using the demo code from the PyTorch examples and adding some data augmentation to make it a bit more robust. So I'll put a link to the sandbox in the description so you can try it out yourself, and I'll also put links to the other code in this video. And that's it for this one. I'll see you guys next time.